A warehouse uses autonomous robots to move inventory. Each robot has a machine learning system that predicts optimal paths, avoids collisions, and estimates task completion times. No central controller directs traffic. Robots negotiate right of way, adapt to congest, and redistribute work when one fails. This works until the system scales to 200 robots and emergent gridlock patterns appear that no individual robot's machine learning model anticipated. The robots are making locally optimized decisions that create globally poor outcomes. This is the multi-agent coordination problem. This is machine learning in multi-agent systems, ML Part 28. Why the system that works with 5 agents breaks at 200, and what machine learning can do about it. Section 1. What machine learning does in agent systems. Agents are autonomous entities that perceive environments, make decisions, and take actions toward goals. Multiple agents operate simultaneously, each with its own objectives that may align or conflict. Machine learning enables agents to function without hard-coded rules for every scenario. Instead of programming explicit responses to every possible state, agents use machine learning models to predict outcomes, estimate values, and select actions based on learned patterns. Perception. Machine learning models process sensor data to understand environmental state. A delivery drone uses computer vision to identify obstacles. A trading agent uses real-time models to detect market patterns. An autonomous vehicle uses sensor fusion to build a representation of road conditions. Perception models turn raw data into structured understanding that agents can reason about. Prediction. Agents use machine learning to forecast how environments will evolve. A robot predicts where other robots will be in 5 seconds based on their current trajectories. A resource allocation agent predicts demand patterns based on historical usage. A negotiation agent predicts counterparty responses to proposals. Predictions inform which actions will likely achieve goals. Decision making. Reinforcement learning models map state to actions by learning which behaviors lead to rewards. An agent explores different strategies, observes outcomes, and updates its policy to favor actions that historically produce good results. The learned policy replaces handcrafted decision trees with adaptive behavior. Section 2. Coordination patterns. Multi-agent systems need coordination when agents affect each other. Independent learning. Each agent trains its own machine learning model based on local observations without considering other agents. This works when agents operate in largely separate spaces with minimal interaction. Warehouse robots in different zones learn navigation independently. The simplicity breaks down when agents must coordinate because each agent treats others as unpredictable environmental factors. Centralized training. A central system trains policies for agents with full visibility into multi-agent environments. Agents then execute their learned policies independently during operation. This works when agents have similar roles and the central system can simulate realistic multi-agent scenarios during training. It breaks when agents are heterogeneous or when training simulations fail to capture real-world complexity. Communication-based coordination. Agents share information through explicit messages when those messages carry semantically grounded assertions rather than raw data values. The coordination layer inherits the precision and audibility properties we discussed in parts 22 and 23. Shared semantic infrastructure reduces the non-stationary problem by giving agents a common vocabulary for reasoning about each other's states without requiring each agent to model the others from scratch. Emergent coordination. System-level behaviors emerge from agents following local rules without explicit coordination protocols. Swarm robotics demonstrate this. Simple local interactions between many agents produce complex collective behavior. Machine learning helps agents learn local policies that lead to desired emergent outcomes, though predicting and controlling emergence remains challenging. Section 3, where multi-agent machine learning gets hard. Non-stationarity. From any single agent's perspective, the environment constantly changes as other agents learn and adapt. A robot learns to navigate around other robots, but those other robots are simultaneously learning new behaviors. What worked yesterday fails today because the other agents changed. Standard machine learning assumes stationary environments where patterns remain consistent. Multi-agent systems violate this assumption fundamentally. Credit assignment. When multiple agents contribute to an outcome, determining which agent's actions deserve credit or blame becomes difficult. A team of agents successfully completes a task. Did all agents contribute equally? Did some agents' actions enable others? Without clear credit assignment, agents struggle to learn which behaviors to reinforce. Scalability. Coordination complexity increases with the number of agents. 2 agents coordinate through simple turn-taking. 20 agents need more sophisticated protocols. 200 agents create a combinatorial explosion where reasoning about all possible interactions becomes intractable. Machine learning approaches that work with small agent populations that work well within that boundary but degrade predictably as agent count grows, because the interaction state space expands faster than any model can learn to navigate, producing coordination failures that appear suddenly rather than gradually. Goal alignment. When agents have conflicting objectives, machine learning training must balance individual performance against collective outcomes. A trading agent maximizing its own profit might create market instability. An autonomous vehicle prioritizing passenger safety might block traffic. Learning policies that achieve individual goals while maintaining system-level properties requires careful reward shaping. Section 4. Real-world examples. Autonomous vehicle coordination. Each vehicle uses machine learning for perception, path planning, and decision-making. Vehicles must coordinate at intersections during lane changes and parking scenarios. The system handles this through a mix of rules-based protocols, traffic laws, which learn behaviors, predicting other vehicles' likely actions, from multi-agent learning, in which vehicles learn coordination policies through interaction, remains an active research frontier. Distributed resource allocation. Cloud systems allocate compute resources across many services. Each service has an agent using machine learning to predict resource needs and bid for capacity. The system must balance competing demands with centralized scheduling. Agents learn bidding strategies that account for other agents' likely behavior and resource constraints. Robotic warehouse operations. As described in the opening, robots coordinate to move inventory efficiently. Machine learning enables each robot to navigate, estimate task durations, and adapt to congestion. Coordination happens through implicit communication, sensing other robots' positions and trajectories, and explicit protocols, preserving paths through shared spaces. Section 5. Why this matters. Multi-agent systems promise to solve problems that centralized controls cannot handle, adapting to distributed information, scaling to many actors, and maintaining operation while individual components fail. Machine learning makes agents capable of autonomous operation in complex environments, but multi-agent machine learning introduces challenges that single-agent machine learning avoids: non-stationary environments, difficulties in credit assignment, and emergent behaviors that are hard to predict or control. The techniques that work for training individual machine learning models often fail when multiple learning agents interact. The federated knowledge infrastructure recovered in Part 20 addresses one dimension of this problem by providing agents with a shared semantic layer they can query without centralized coordination. Agents that can share an ontology share a vocabulary for reasoning about each other's states and intentions, which reduces the non-stationary problem without requiring agents to model each other's full internal state. Understanding these challenges explains why agent systems that work with a few agents break at scale, why simulation results do not always translate to real deployments, and why some coordination problems still require hybrid approaches that combine learned behavior with explicit protocols. In closing, machine learning enables multi-agent systems by giving agents perception, prediction, and decision-making capabilities. Coordination patterns range from independent learning to communication-based protocols to emergent behavior from local rules. The challenges are non-stationarity, credit assignment, scalability, and goal alignment. Understanding machine learning's role in agent systems explains how distributed intelligence can solve complex problems, but also why multi-agent coordination remains harder than single-agent learning. In Part 29, we will cover build versus buy decisions for machine learning systems and why the semantic layer significantly changes the calculation when systems you are evaluating need to reason over formal knowledge rather than just process features.